Imagine a weapon so fast that by the time radar sees it, it's already too late. We're not talking about supersonic, we're not even talking about ballistic missiles that arc through space. We're talking about hypersonic systems, vehicles that fly at Mach 5 and beyond, more than 5 times the speed of sound. At those speeds, the air itself becomes a weapon. Metal begins to glow. Shock waves compress the atmosphere into plasma. But how do these systems actually work? Let's break it down. Without hype, without politics, just engineering. Speed in aviation is measured in Mach numbers. Mach 1 equals the speed of sound. Mach 2 equals twice the speed of sound. Mach 5 equals hypersonic threshold. But hypersonic isn't just very fast. Once you pass Mach 5, physics changes. Air can no longer smoothly flow around a vehicle. Instead, it compresses violently. Temperatures on the nose can exceed 2,000 degrees Celsius. At these speeds, oxygen molecules begin to break apart. Plasma forms around the body. Flying hypersonic isn't about power, it's about surviving the heat. There are 2 primary designs used today. These start like traditional rockets. A booster rocket launches the vehicle high into the atmosphere, sometimes near the edge of space. But instead of following a predictable ballistic arc, the payload separates and begins to glide back toward Earth at hypersonic speed. The key difference? It can maneuver. Unlike a traditional ballistic missile that follows a fixed parabolic path, a glide vehicle can shift direction mid-flight. It skips along the upper atmosphere, changing altitude and heading. That unpredictability makes tracking far more difficult. These don't rely solely on rockets. Instead, they use an engine called a scramjet, short for supersonic combustion ramjet. And this is where things get extremely complex. Normal jet engines cannot function at hypersonic speeds. At Mach 5, incoming air slams into the engine at extreme pressure and temperature. A traditional turbine would literally melt. A ramjet solves part of this problem by having no rotating compressor. It compresses incoming air purely through forward motion. But even ramjets struggle past Mach 4, so engineers developed scramjets. A scramjet allows air to pass through the engine at supersonic speeds without slowing it down before combustion. That sounds simple. It's not. You are igniting fuel in airflow, moving faster than a rifle bullet. The combustion must occur in milliseconds. Too slow, and thrust collapses. Too fast, and the engine destabilizes. It's like lighting a match inside a hurricane and keeping it stable. Speed isn't the hardest problem. Heat is. At Mach 5 and beyond, friction with air generates extreme thermal loads. Leading edges can reach temperatures hot enough to weaken steel and soften titanium. This is why hypersonic vehicles rely on advanced ceramic matrix composites, heat-resistant alloys like Inconel thermal, protection coatings. Even shape matters. Sharp edges generate higher heat concentrations. Blunt designs spread heat but increase drag. Every curve is calculated to balance aerodynamics and survivability, because at hypersonic speed, you're not just flying through air, you're flying through fire. Another challenge few people think about: communication. At hypersonic speeds, plasma forms around the vehicle. That plasma can interfere with radio signals, creating what's called a communications blackout. So how do these systems navigate? Most rely heavily on inertial navigation systems, internal sensors that calculate position based on motion. In terminal phases, some systems use radar or infrared sensors to refine targeting. But remember, at Mach 5+, every second matters. At those speeds, a vehicle can travel a mile in under 2 seconds. There's very little room for correction. Traditional ballistic missiles are fast but predictable. They follow an arc. Defense systems calculate where they'll be and intercept. Hypersonic glide vehicles change that equation. They fly lower than ballistic missiles. They maneuver mid-flight. They compress detection time dramatically. Imagine you have minutes to react. Now imagine you have seconds. That's the shift. And it's not just about speed. It's about unpredictability. Radar systems are optimized for certain altitude bands and trajectories. Hypersonic systems blur those assumptions. The result? Defense becomes significantly more complex. Of course, engineering never stands still. Next-generation tracking systems are being developed that rely on space-based sensors, multispectrum detection, advanced predictive algorithms. Some research even focuses on directed energy systems, using high-powered lasers to counter high-speed threats. The technological race isn't just about who can fly faster, it's about who can see first. Because in high-speed warfare, awareness equals survival. Hypersonic systems represent more than a new category of weapons. They represent the intersection of advanced propulsion, materials science, computational modeling, precision guidance. They push engineering to the limits of thermodynamics. They force radar systems to evolve. They reshape strategic planning. But they are not magic. They are physics, applied at extreme levels. At Mach 5 and beyond, the atmosphere becomes an obstacle course of heat, pressure, and instability. To build something that survives there, that's the real achievement. Hypersonic systems work because engineers learned how to harness airflow instead of fighting it, manage heat instead of avoiding it, calculate trajectories in fractions of seconds. They are not simply faster missiles. They are controlled shockwaves riding the edge of physics. And the real story isn't just about speed. It's about how far engineering can go, when pushed to its absolute limits. If you found this breakdown useful, make sure to subscribe for more deep dives into modern defense technology. And here's the question for you. Is hypersonic flight the future of global aviation, or just a stepping stone to something even more extreme? Let me know what you think.